Okay, so now that we finished chapter 7, we're going to go backwards to chapter 6 now, and work through the material there. So we're going to get started with chapter 6, section 1. And this is on areas and volumes. So 6.1 is on areas, area between two curves. Okay, so let's just go through a couple of these slides. Okay, areas between two curves. Consider something like this. Let me zoom in on it a little bit. So notice what we have here. We have a function here in red, this little red function, which is defined as y equals f of x. Right? We still have a y-axis and an x-axis as is traditional. And then we have this blue function over here, which is the g of x function, y equals to g of x. Good. So we're interested in the area between these two functions. Okay, consider the region S that lies between the two curves y equals to f of x and y equals to g of x, and between the vertical lines x equals to a, right? Remember, vertical lines have the notation of x equals the constant. So this is the vertical line x equals to a, and this one is the vertical line x equals to b. So we want this region shaded in blue, right? That's what's being defined here by all those conditions. And this is where f and g are continuous functions, and where f of x is always greater than or equal to g of x for all x in the region between a and b. Right? So at least in this little region that we're interested in, it is always true that the f of x function is greater than or equal to the g of x function. That's not always going to be true, because as you can see over here, they swap roles eventually. But for the domain that we're interested in, it's always true that f of x is greater than g of x. That's important because when we want to find the distance between them, we subtract them in this particular order. The larger value minus the smaller value, and that'll guarantee us a positive answer. Right? In order to approximate that area, we create these little rectangles. Right? That's the process that we established before. The only difference is that before we were only looking at the distance between a function and the x-axis, whereas now we're looking at the area between two functions. Right? So we create one individual rectangle. The width of it is going to be delta x, right? And then we think about its height. Its height is going to be equal to f of x minus g of x, and then that'll give us the result that we want. And it has to be in this particular order just because the way the picture was drawn. The f of x function is the larger value, and the g of x value is the smaller value. Notice that this equation is always going to give you the distance between the two, even when they're both positive answers or when they're both negative answers. Right? Like, for example, just to make sure, for some reason that sometimes becomes an issue. Just to throw some numbers out, let's just say that at this point it's some positive answer. Let's say at this point the output of y is an 8. I don't know why it's so thick. The output of y, let's say that it's an 8 at that point, and then right below there, at that point, let's say that height is a 3, then the distance between them would be a 5, right? It would be 8 minus 3, right? If all of these were the result of an x input of, and again, I'm just making up some numbers to highlight this. Let's say that this was a, I don't know, 11. Then this 8 would be f of 11, which is the 8, right? Since this red one is the f of x function. Whereas this 3 would be the g of 11. And so that 5 can be expressed as f of 11 minus g of 11, which gives us the value of 5. Good. That will also be true in the cases where we have negatives. So let's say that we have a value here, went a little higher. So let's say that at this point we have an output, a height, a y value of, well, let's say a different number, say 13. And then down here, let's say that right at that point, we have a output value of, say, negative 4, right? because it's below the x-axis, so we know it's a little bit negative. And let's say all of this happens at, I don't know, 7. Just making up some numbers. So that means that this 13 would be f of 7 is giving you the 13. Good. And this negative 4 would be g of 7 is giving you that negative 4 right there. And so the distance between the two would be 13 and then the 4. We know the answer should be 17. And so if we do 13 minus negative 4, we'll get the result we want. This would be equal to 13 plus 4, which is a 17. And so this 13 is g of 7 minus, and then this negative 4, oops, sorry, the 13 is an f of 7. F of 7 is the 13 minus the g of 7 is the negative 4, and so the equation holds, right? So whenever we want the distance between the two, this is the formula we want. F of x star minus g of x sub I star, right? The same input value into both functions, so subtract them in this order, and we're going to get the difference between the two. Good, good, good. Okay, I think that's pretty good. So this is really messy now, so let me just clear out all of this stuff here. I was just highlighting that difference formula will always work as long as we are careful to put the equation, the function which results in the higher value first. Okay, so that equation will always be true. So that's just highlighting that this part is true. Good, it'll give us that height. Okay, so for one specific rectangle, the area approximated in this little blue rectangle is going to be the height, which is this thing, times the base, which is this thing. Multiply them together, we'll get that, right? And then we want to do it for several rectangles and kind of get an approximation, which would be something like this. For all of these, we always assume that the base is always the same. The base for all of these things is always going to be delta x. Right there, the base is always the same, delta x. But the thing that is different is the height, and the heights will vary based on the input value of x that you choose. So it's going to be a function of x. Right? So that's what this is right here. Right? So we can come up with some new function, which is the heights. The heights of x sub I star are equal to f sub x sub I star minus g of x sub I star. In this order, because we know that for the particular domain we're interested in, the f of x is higher, it's bigger, it has larger values than the g of x function. Right? Any questions so far? No? Looks familiar? This is very similar to integrals, right? When we first introduced integrals. So the approximated area here is going to be a sum of rectangles, where each rectangle is going to have this base and a height, which is a function of x sub I star. Right? So for each rectangle, we're going to pick one randomly chosen value in the domain inside that rectangle. That's going to be the x sub star 1 for the first rectangle, x sub 2 star for the second rectangle, x sub 3 star for the third rectangle. Right? Let me point that out. So let's say in this approximation here, we're going to randomly pick one value in here in the first rectangle. Say, for instance, well, let's erase these things here so that they don't get in the way. Right? It could be anywhere inside that first rectangle. So let's say, for example, maybe it's right there for the first one. Maybe this one is x sub 1 star. That takes care of the first rectangle. And then for the second rectangle, somewhere inside the domain of the second rectangle, anywhere randomly selected, say it's that one right there, that little spot. That would be x sub 2 star. Right? And so we do that for every rectangle. Inside every rectangle, we choose one value inside there. And so the area of the first rectangle is going to be equal to f sub x sub 1 star. That tells me the height times delta x. That's the area of the first rectangle. Plus the area of the second rectangle is going to be f sub x sub 2 star. That'll tell me the height of the second rectangle times delta x. Good. Plus the area of the third rectangle, and so on and so forth, until you get to the nth rectangle out here. So this would be f of x sub n star. That'll tell you the height of the nth rectangle times the base of the nth rectangle. Since all of these bases are the same, we can factor them out. And so we end up with f x sub 1 star plus f x sub 2 star plus dot 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 all the way out to f sub x n star. And then all of that gets multiplied by delta x. Good. And then this guy here, we're just going to turn that into a Riemann sum. That's the Riemann sum of f of x sub I star, where I runs from 1 to n, right? That's this whole thing right here. And when you're done with all of that, you can multiply the whole thing times delta x. Good. Now, it doesn't really matter whether we think of this delta x as being multiplied times each of these, like up here, or if we factor the whole thing out and then multiply it sort of on the outside. And just to make sure it's clear that it's sort of on the outside, we can also stick it out in front. We can also say it's delta x times the Riemann sum as I goes from 1 to n of f of x sub I star, right? Either one. And the reason we're allowed to do that is because this is a different variable, right? So this x sub I is this countdown, right? X sub star, this, note that this is a little star, x sub star I, that's different than this x, right? This is just a constant. Delta x is a constant that we can kind of factor out. But either way. So that's just maybe a little bit more explanation on where this guy is jumping to over here. So, I just realized that I was using the f. I meant to use the h sub xi this entire time because that represents my height, right? I kept saying f instead of h. Well, that's egg in my face. So let's go back and fix this. So for all of these, I meant to say that it's the height of it, and based on how I'm defining my h, this should be h of x sub I. That tells me the difference between the two. That's this. Times the delta x, h of x sub 2 star times delta x, and then h of x sub n star. Good. And then let's fix this as well over here. So now if I factor out that delta x, I'll have h there, and h there. Right? So these all tell us the difference between those two functions, which is going to be the height of my rectangle, which means that this is going to be an h there, and therefore the same thing as this h here, h. Good. And so finally I could say, well, the h was the difference between the two, so I can also just say that it is the Riemann sum as I goes from 1 to n of f of x sub I star minus g of x sub I star times delta x. And just like down here, we can also then just factor out that delta x and say that this is the sum, as this goes from 1 to n, of the difference of, between the two. F sub I star minus g of x sub I star. Good? Questions, questions, questions? Questions, questions, questions? Okay, so that's where this formula is coming from. So the area trapped between two curves, in order to find it, we need to subtract it, be careful to do it in the right order, times delta x. And then that will translate into something pretty familiar. We want to let, this is an approximation using n rectangles, and then we want to let n go to infinity, right? We want to do the limit as n goes to infinity of this Riemann sum, and we'll see that that becomes the area between the two curvatures. Right? So the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of x sub I star minus g of x sub I star, right? This will be the height of each rectangle, times delta x. Right? Again, this Riemann sum does not affect this delta x. This is just some constant. Well, once we find for a specific value of n, this is a constant. But then it does get affected by this limit, right? Because as n goes to infinity, the delta x's get smaller and smaller and smaller. Good, good, good. Okay, well that is just exactly our definition for integrals. So this is simply stating that the area is equivalent to the integral from a to b of f of x minus g of x delta x. I'm sorry, dx. Good, 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 good. Notice that this is exactly what we've been working with if you consider the g of x function to just simply be the x-axis, or g of x equals to 0. Right, so we've been working with this in a sort of more simplistic way. This is kind of like when you first realize that all numbers are actually fractions. You've been working with fractions your whole time, right? Because you learn fractions and you're like, oh, this is a brand new thing. I've never thought about 3 over 5 or 7 over 2. But if you think about your whole counting numbers, 1, 2, 3, 4, 5, right? We can always think of putting a little 1 underneath there. And like, oh, actually, we've been working with fractions the entire time. It's just that we've been working with fractions that all have a 1 in the denominator. And then things become simple, right? Common denominators, they all have a 1. And so it's similar to that in that all the integrals we've been working with just have this invisible minus 0 out here, and then everything stays the same. Questions, 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 questions? Good, 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 good. So in the case where both f and g are positive, we can see a nice little figure here that also kind of confirms the formula for us. So if we have, let me zoom in a little bit more here. Let's have a case where both f and g are both positives. They're both above the x-axis. So by the prior formulas that we were working with, it was always the area between the function and the x-axis. So if we just simply integrate from a to b of f of x, right, assuming f of x is integrable, that the integral exists from a to b, that'll give you the entire area of this whole thing. Let me put it in, let's put it in green. So this right here is the area underneath the f of function trapped between the f of x function and the x-axis between a and b. So that gives you this whole area all the way down to there. Okay. And now the g of x function, that gives you the area trapped between the g of x function and the x-axis, that'll give you this area in red right here. Right? And so now what happens if we take the entire area in green and subtract off the area in red? Well, you're going to get exactly what you want, which is going to be this area trapped between the two, which is this purple part in here. Right? So this part is the red, this part is the green, and if we subtract them, we'll get exactly what we want, the area in purple. Purple area. Good. Questions, 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 questions. There is a nice little applet to exemplify this over the head here. It's like a little applet to kind of show this off. Let's see if we can fix this to say that. Nope, we don't want that. Plus 2 maybe? Okay, that looks like that, right? Okay, so if we want to find the area between these two functions, between, -1 and 1. This thing is not that user-friendly, so, okay, here we go. Between -1 to 2, okay, from -1 to 2, and then we can decide how many rectangles. So let's begin with 10 rectangles. So there's an approximation using 10 rectangles. Right, so for the 10 rectangles, we got to find the heights, the difference between the two. So we got to take this value along the f of x function and subtract off the value along the g of x. Is that what it's called? Yeah, g of x. In this order, because for this little region between -1 and +2, the linear equation is always bigger than the quadratic one, right, for that little region. Good, good, good. Okay, so here's one approximation using 10 rectangles. Of course, we want to do better than that. How about 15 rectangles? That's getting better. It's an even better approximation, so we want to do even better than that. Let's do 25 rectangles. Right, so the more rectangles we use, the better the approximation. But it's always going to be an approximation as long as we stop at any constant for n. Even if n is really big, n is 1 billion, that's still an approximation. A very good approximation, but still an approximation. Good. However, once we apply our rules for limits and we let the limit n go to infinity, if that limit exists, we no longer have an approximation, we have an exact value, right, at infinity, if it exists. Good. It might not exist. We might run into a problem. Therefore, the best we could do in some cases is just to get a really good approximation. So just let n be a really big number. Good. Good, good, good. Questions, 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 questions. No, no, no. Okay, so let's move on over here. Here's an example. Find the area of the region bounded by y equals to e to the x power, bounded below by y equals to x. So first of all, they're giving you a nice hint that this function is greater than this function. In some cases, that might be part of the work you have to do to decide which function is above and which function is below the other. So that might take a little bit of work. So bounded by this above, bounded by this below, and then bounded by x equals to 0 and x equals to 1. This is a nice little picture of this whole thing. Okay, so here it is. So begin by creating one little rectangle, right? Whenever you run into these questions in this chapter, it's a really good idea to get a little mental picture of what you're doing and let your picture guide you, because they will get really, really confusing. This is a pretty tough chapter for people, I think. So even if they're easy, you know, go through the trouble of doing this, because that kind of will establish the pattern for you. You'll get comfortable with it, and once they get really hard, you'll have something to fall back on, a process. Okay, so we've established this function. This is kind of like our f of x function, right? Oops. Come on. So this red one, I hate computers. So this red one is kind of like our f of x function. And then this blue one down here is kind of like our g of x function. Right? So we know that the height of one of these rectangles, that height function, is going to be equal to f of x minus g of x So for us, it's just going to be equal to e to the x power minus x is that height. Good. And this is valid for, come on, this is x trapped between 0 and 1. That's all we're interested in, so it doesn't really matter what happens beyond 1 or below 0. We don't really care. In this region, that's all we care about. So we have one individual rectangle, the area of this rectangle is just going to be equal to this function. Okay, so I think we're ready to set up our integral. Our integral is going to be equal to the integral, I'll say area is going to be equal to the integral where x ranges from 0 to x ranges to 1. And also, I think it's really a good idea to start labeling your limits of integration, including the variable of integration, because again, they're going to get confusing a little bit. We're gonna sometimes switch from x to y, and I think it might be useful to get into the habit of putting your variable of integration in the limits like this. Okay, so x is going to go from 0 to 1, and we're going to have a e to the x power minus x be our sort of our heights, and then we have dx. Good. Any questions? Any questions? Any questions? No? Okay, well, luckily this is a really, really easy one to actually integrate. So this is just going to be equal to e to the x minus 1/2 x squared, right? And then guessing and checking, let's see, the derivative of this is exactly e to the x. And the derivative of this is going to be, yep, x to the first power. This gets evaluated as x ranges from 0, x goes to 1. So this is going to be equal to e to the 1 power minus 1/2 1 squared minus e to the 0 power minus 1/2 0 squared, which is just going to be e and minus 1/2 minus e to the 0 power is equal to 1. And 1/2 times 0 squared is still going to be 0. So minus 1. Minus 1. And then if we get a common denominator between these two, so let's multiply this by a 2 over 2. Turn that into a 2 over 2. So we get minus 1 minus 2. We get a minus 3 over 2. E minus 3 over 2. Good. Good. And we can just get our calculator and put a decimal approximation if we want it. So that would be e minus 1.5 is going to be approximately 1.2183. Any questions?
I have a quick question.
Yeah.
So after you wrote the integral, in the parentheses e to the x minus x, and then the next line where you have e to the x minus 1/2 x squared, to get to that point, did you use the chain rule?
Are you talking about this right here?
The next line. Yeah, the minus 1/2 x squared.
1 minus 1/2
ex minus 1/2 x squared.
Mm-hmm.
That portion that you're circling. So that you use the chain rule to get that? Or did you just rewrite that as because I don't see where the squared came from.
It's the antiderivative of this, right? The integral.
Okay.
So then the antiderivative of x is going to be some function whose derivative equals this guy. So I was just using our guess and check method, right? So the derivative of this, you bring down the 2, that cancels with this, giving you a 1. And then you subtract 1 from the exponent, and that's how you get x to the power of 1.
Okay, yeah, thank you. I forgot about that. That's right.
Sure, no problem. Let's see. Did the author do something similar, or did I mess up somewhere? Okay, we got the exact same answer. So, yep, so we set up our integral from 0 to 1 of the 2. Okay, so we have to be careful and make sure we put this one first, this one second. If I had done it the other way around, if I accidentally put x minus e to the x power, then what happens is my answer is going to be off by a sign. I'm going to end up with this minus that, which means I'll end up with 1.5. Wait, no, I'll end up with 1 minus the difference between these two. And so you'll be off, right? So we have to be careful. The order is important with these questions. Good. Good. Okay, so in figure 4, we drew a typical approximating rectangle with a width of delta x as a reminder of the procedure by which the area is defined, right? So just begin by drawing a typical rectangle somewhere in the middle. Think about where the width of it is and where the limiting factor is going to come, right? We're going to make the delta x's super, super, super small. Thin, 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 thin. So that means we're going to end up with a dx, right? And then we need some function that tells me the heights of those. So it'll be some value of, some function of x, which gives me an output of y for the red function, and some function of x, which gives me an output of y for the blue function down here, and then we subtract them. Good, 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 good. So one way to kind of refer to them as the top function and the bottom function, it just makes it a little easier. So y sub t is the top function versus the y sub b is the bottom function. I also often refer to them as the roof and the basement, or the ground level. Ground level often kind of maybe conjures up images of the x-axis though. So the bottom function and the roof function, or the top function, just language to try and refer to the function that is above and what the function is that's below. Good, 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 good. Okay, then the areas of the typical rectangle. Okay, so kind of sticking to the notation from before, going back to establishing it as a Riemann sum of approximating rectangles, right? The limit as n goes to infinity of, and here's your approximating rectangle, which is then exactly the definition of an integral, which is this guy, right? So it's just kind of reestablishing the same thing. Now we have to be careful in some cases because the function which is on top and the function which is on bottom might not be consistent all the way throughout your domain. So here is an example where maybe this is like a sine function, this is like a cosine function perhaps, something like that. And so the roles alternate. Sometimes this function is on top, sometimes it's on the bottom. So what we have to do in cases like that is break up our little problem, right? They might just ask us what's the area between these two functions, but we have to know better than that. We have to know that in order to do it, we're going to have to break it up into 3 different regions where the rules vary on region to region, right? In this region, this function is, the red one is on top, the blue one is on bottom, so I can write it in that order. That would be, well, okay. So looks like the red one is f of x. So in this little region of s sub 1, f of x is greater, so it would be f of x minus g of x. Let's write down. So in this little region, let's go right there, and then this little region right there. So for this part of my domain, in this part of domain, it's true that I'm going to have f of x minus g of x, because the f of x is larger. Same thing with this region over here. I'm going to write down f of x minus g of x. But for this middle part, it's the other way around. It's going to end up being g of x minus f of x. Good. So you can see how some of these problems are going to get really complicated because you need to figure out when one function is greater than the other. One way to do that, as you can see, is to figure out when they equal each other, right? That's a potential place where there might be a crisscross. So if we can figure out when these two functions equal each other, or equivalently, if we subtract them and think of their difference, right? If we define some new function h of x to be the difference between the two, which is maybe f of x minus g of x, then the places where they cross each other is the same thing as the places when the function equals to 0, right? When they equal each other, this function equals to 0, which means it's a 0 of the h of x function. So that might be a useful way to figure out where they cross. And then once you do that, that breaks up your domain into little regions, and then you have to figure out which function is larger, which one is going to be your top function, and which one is going to be your bottom function for each one of the sections. Good. Okay, so if we have the absolute value of f of x minus g of x in absolute values, then we have to break it up this way. Figure out the places where f of x is greater, right? Wherever f of x is greater than g of x, we're going to subtract it this way, so we get a positive number. And whenever the g of x function is greater, we subtract it in this way, again guaranteeing that we get a positive answer. Good. So we have the following expression for a. The area between the curves y equals to f of x and y equals to g of x, and between a and b of this, area equals to the integral from a to b of the absolute value of f of x minus g of x dx. When you value it in the integral, we must split the integral into little corresponding values, a sub 1, a sub 2, a sub 3, dot, 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 such that we can rewrite this absolute value. We can get rid of the absolute value by rewriting it in the proper order in the regions that correspond to you giving you a positive answer. And so sometimes it'll be f of x minus g of x, and sometimes it'll be g of x minus f of x, depending on which function is higher in each individual area. Good. I hope that kind of made sense. So let's look at this problem, this application. Find the area of the region bounded by the curves y equals to sine x and y equals to cosine x on the domain as x goes from 0 to x goes to pi over 2. Right, so this is a nice straightforward one, and even if, let's just use technology because I will absolutely butcher this no matter what happens. Yeah, this guy. Okay, so let's go to Desmos. So we want to graph y equals to f of sine of x and cosine y equals to cosine x, like that. Okay, so let's just label them as f of x equals sine x, and g, it's not g of x equals cosine x. And let's see, does it let me do x equals 0? Okay, that's that guy. And x equals to pi divided by 2. All right, let's get the right colors going here. Let's make this, make it that black, make that brown. Let's make this red. Let's make this red. Okay, and let's zoom in. Okay, so this is what they want, right? There is a way to shade in here. I forgot how to do it. Okay, well, anyway, I give up. So what we're talking about is this little region, right? We have a cosine function here in blue. We have the sine function in black, and we want to find the area between the two. I think, in fact, I already had a nice little picture of that anyway. Okay, so it's going to be something that looks roughly, that's where I butcher it. Okay, so we have a sine function that's going to start here, go up, come back down, and go this way. Good. And then we have a cosine function that starts up at 1 and comes down like this and ends up there. Ah, see, this is why it's going to be ugly, because it needs to be that it crosses and then they end up at opposite ones. I don't know, something like this. It's ugly, but we end up with something that looks like that. Sort of, kind of, sort of, kind of. I can't over this. All right, let's try this again. So hard to even go straight on this thing. Okay. So let's say one function comes up here and comes down here, and this kind of thing. And then the other function is going to start here and come here. I don't know, something like that. And so we have this, and we have this right there. Okay. So we want to figure out that spot right there, and we're gonna go from there, which is going to be pi over 2, and this guy is 0. This is the x, and this is our y. Good. So this function here is sine of x in blue, and the green one is cosine of x, cosine x. Right, so this one's going to continue down here and bottom out around there and do that kind of thing. Good. Questions, 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 questions? So when it said the area between the two, it really translates into finding the absolute value distance between the two functions. Good. Bounded by this function between the... Okay, so the area between the... bounded by the curves, so the area is equal to the integral between 0 and pi over 2. Like I said, I think it's a good idea to get used to putting the variable of integration in the limits like this, so that when we switch them around, you have an easier time tracking what happened. Okay, and so this is going to be the absolute value difference between the sine function and the cosine function. So inside these absolute values, it doesn't matter which one you write first and which one you write second. Right? But now, in order to get rid of those absolute values, now we have to think about it. And so this will become equivalent to the integral from 0 to, and now we have to figure out when do they equal each other, right? And so luckily that's going to be one of our standard results. That's just going to be equal to pi over 4. Right? That's because sine of pi over 4 is equal to cosine of pi over 4. Good. So now this goes up to pi over 4. And in that little region, the cosine function is bigger. So I'm going to do cosine of x minus sine of x. No absolute values. I'll put parentheses because it needs to have a dx there. And the dx applies to the whole thing. But no absolute values. Plus, and now I have to do the other integral over here. And the other integral is going to be the integral between x ranging from positive pi over 4 all the way up to x equals to pi over 2. And then in that little region, it's the other way around. Sine is bigger minus the cosine. Sine of x minus the cosine of x, parentheses, dx. Any questions? No? So we broke it up into two areas. A sub 1 is this area here, whereas A sub 2 is this area here. And this whole integral is going to give me the result of A sub 1, whereas this whole integral is going to give me A sub 2. I add them together, and it will give me the area between the two curves. Area bounded by the two curves. Okay, now the actual integral, not too bad. Very easy antiderivatives, right? So derivative of sine is cosine, so that'll be sine x. The derivative of cosine is minus sine, so it'll be cosine x. Evaluate it as x goes from 0, x goes to pi over 4, plus, and then the derivative of cosine is negative sine, so it should be negative cosine x. Give me the antiderivative for that guy. Minus sine x. Come on. The derivative of sine is cosine, so we get that guy. Evaluated as x goes from pi over 4 to pi over 2. Questions? Okay, so let's evaluate this one. We just stick a pi over 4 in both of these. So it'll be sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. Okay, so that's that first one. And that whole thing, well, we can factor out this minus to begin with and say that that's going to be minus parentheses. And now, so let me just put that here. I'm going to make that a minus, plus, plus. So it'll be minus parentheses cosine x plus sine x. Okay, so this minus comes from there. And now it's the addition of these two. So I'll have cosine pi over 2 plus sine of pi over 2 minus cosine of pi over 4 minus, plus, come on, sine pi over 4. What did I do? This thing is there. Okay, so plugging in a pi over 2 to both of them, cosine sine minus cosine sine.
I think that isn't the last one pi over 2. Isn't it plus sine pi over 2 for the last one?
So I applied a pi over 2 to both of these, and that's this. Cosine pi over 2 plus sine of pi over 2 minus, and then cosine of pi over 4 plus sine of pi over 4. So I think this is right.
Oh, I'm sorry. Yeah. Hey,
We're good?
my fault.
It's easy to get confused. I'm not totally confident either. Okay, so let's simplify some of these. This guy is a 0. That's fun. Cosine of 0 is a 1. That's easy. Okay, leave those alone for a second. Now, cosine of pi over 2, sine of pi over 2. So cosine of pi over 2 is going to be equal to 0. And sine of pi over 2 is equal to 1. Good. And so what do we get? We end up with, so these are all root 2 over 2. Let's just make them on here. So these are root 2 over 2, root 2 over 2, and these are also going to be root 2 over 2 and root 2 over 2. Okay, so I end up with a root 2 over 2 plus a root plus a root 2 over 2 minus a 0, okay, forget that, minus 1. And then we end up with a minus from here, minus 0, okay, so let's put it in parentheses. I'll end up with a 1, and then minus root 2 over 2 minus root 2 over 2, right? Distributing this little minus across these two. So just got to be careful with all those minuses running around everywhere. So we'll end up with a minus here and then a plus plus. So root 2 over 2 plus root 2 over 2 minus 1 minus another 1 plus root 2 over 2 plus root 2 over 2. So there will be 4 copies of this root 2. So it'll be 4 root 2 over 2 minus 2, which we can put as a common denominator. A 1 there, put a 2 there, put a 2 there. That makes it 4, so it'll be 4 root 2 minus 4. Oops. So it'll be 4 root 2 minus 4 all over 2, which means we can factor out a 2 and cancel. Oh, duh, what did I do? I could have just reduced this here. That was silly. Could have just reduced this there and then left it all. Either way, we get our final answer of 2 root 2 minus 2. 2 root 2 minus 2. Good. Questions? Can I match up with, yeah, 2 root 2 minus 2. Good. So match with the author. Zoom out a little bit. Whoa, zoomed out way too much. Zoomed in too much. This thing's annoying. Any questions? No? Okay, let's look at the author's result. Right? So same kind of graph, almost the same, only better. Right, so notice the key was to figure out when they crossed. Luckily, sine and cosine are classic functions, so that wasn't too hard. But in other examples, it's easy to see how that can get a little tricky. Figure out where they cross. Figure out which function is the top function, which one's the bottom function for each individual region. And then we integrate. Keep track of all those signs everywhere so we don't make a mistake. Also, we could have noticed in symmetry, by the way. We could have said, well, this blue region and this orange region are going to be the same, based on symmetry. So you could have just found the area of one of them and doubled it. Right? So that's the other potential solution. Find the area of the first one, double it. That'll give you the area of the whole thing. Good. And finally, sometimes we might have to switch things around, because if we're trying to find this region here, for example, then notice that we cannot do rectangles like this, because the rules of which one is on top and which one's on bottom change. So let me kind of recreate this over here. So let's say I had a function that did this, and then another function that kind of did this kind of thing, say that, and I wanted to find the area between the two. If I tried to come up with rectangles that go this way, then things are weird. Like over here, for example, I have a rectangle where the height of the rectangle is not determined by subtracting two different functions. Right? The green one is the f of x function, the black one is the g of x function, so that looks weird. And then you have little regions where, at any rate, even if we have a thing here, so we have something like that, this goes up there. We have a little region over here where maybe this rectangle, again, is following a different set of rules than a rectangle right below it. Right? So going in this direction is just going to cause all kinds of problems. Sometimes it is a matter of the black function minus the green function, but then over here we might have another rectangle where it's the other way around, the green function minus the black function. So it causes all kinds of problems in this direction. However, if you just tilt it around and think of a rectangle in this direction, then we always have the same rule. This red one is the biggest function, and the blue one is the smallest function. So this language of top and bottom gets a little bit confusing when you tilt it on its side, because now we care about the one farthest to the right and the one farthest to the left as your top and your bottom. So you can also just kind of tilt your head and think of it that way. But in this direction, like this, then each sample rectangle will always follow the same rules. It's always the red function minus the blue function to give you this distance across in this direction. And then the widths are going to be delta y's, right? Because this is the y variable. Good. So we always want red minus blue. But notice that in this case now, we're looking at subtracting x values. Right? The input is going to be some y value, right? So we're going to input some y value, y sub star, and then for that y sub star value, there's going to be some particular x sub star value that is connected to this blue function, which is the bottom one. And then likewise, there'll be some sort of x sub top function. Right? And then if we subtract the two of those, it'll give us the distance, the length of the rectangle that we're looking for. Good? Okay, so we'll do a couple like this, or at least one like this. We'll look at the homework. I don't think there's any more in this slide. No, we're basically done. So I'll get another example like that in a second. But remember that when we graph it, I like to just kind of begin by drawing my little rectangle and thinking about which one's my limiting variable, right? The delta x versus the delta y, and I ultimately want all these rectangles to get skinnier and skinnier and skinnier so that I can end up getting a better and better approximation. That's how I know that I want a delta y, which means my variable of integration is going to be a y. Good. So that means I need a function where we input a y and the output is an x, and I want to be able to subtract the x values in the perfect order where I get the largest x value minus the smallest x value. Good. Sort of, kind of, maybe. Good, 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 good. So if the red one is f, the f of y function, and the blue one is the g of y function, then what I would subtract them in this order, where this is going to lead to the x sub t value, the top one, and the g is going to lead to the x sub b value, the top bottom, or we can turn our language into the right and left since it's the biggest one. So that's what your author has done here. Instead of calling it the top one, he calls it the right one. And instead of calling it the bottom one, he's calling it the left one. So right and left. Right? So the r, x sub r, the right one, minus the x sub l, so the larger one and the smaller one. Good. Questions, 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 questions? And that'll give you that region we want. Okay, so let's look at some examples, and I need to come up with this thing. This is Has anybody started the homework? Is there any suggestions on anything? Anybody have trouble with 6.1? Right, 4. 4. Looks like a 6.3. Okay, here we are, 6.1. So the first few are really nice because they just give you the graph so that you can see from the graph which one is the top function, which one's the bottom function, and it makes it really easy to set up your integral. Good. So for example, let's just set up number 2. We won't have to take it all away. I just want to set up, find the area of the shaded region. Okay, so for number 2, Chapter 6, Section 1, number 2, we want to set up that integral, that shaded region. We want to integrate, and then the top function is that red one. It looks like it's going to be e to the x power minus the bottom function, which is that blue one, x e to the x squared function, right? And then we're going to have a dx, and so the limits of integration go as x ranges from 0 all the way out to x equals to 1. Right? We're going to have little rectangles that go this way. Right? I should have set up a little iconic rectangle. Right? So the iconic rectangle is going to be one that looks like this. We have this that goes that way, and then we have this thing that comes up like this and goes that way. So we want that area in between. And so one rectangle that we're going to be working with is going to be something like that. It's going to have a delta x, and its height is going to be the red one minus the blue one. Right? So this is the setup for the Okay, well, luckily, this looks really ugly, but luckily there's a nice little X there because it makes life a little easier for this guy. Think about what this is going to be. So the first one's easy. It's just going to be e to the x. And this one, it's going to be sort of guessing and check method. If I use that, I know its derivative is going to be, to repeat it, times the chain rule would throw in an extra 2x, right? And we did want that. So all we have to do is think about canceling out that 2 to give you a half, right? So kind of off on the side work. I'm thinking the derivative with respect to x of e to the x squared, like this, is equal to e to the x squared times, and now I'm using the chain rule, the derivative of the exponent, which is going to be equal to e to the x squared times 2x. So I know the derivative is this guy, right? And then, so kind of guessing and checking, find a function who gives you this derivative. I'm pretty close. It's this one. So that's why I introduced this extra 1/2 there to cancel out this 2. And now I know that the derivative of this whole thing gives me exactly that. Good. The whole thing gets evaluated as x ranges from 0 to x goes to 1. And so I get e to the 1 power minus 1/2 e to the 1 squared minus e to the 0 minus 1/2 e to the 0 squared. Okay, so this is going to be e to the 1 power minus 1/2 e to the 1 power minus e to the 0 power is a 1 plus, right, we have a minus situation, so that'll be a plus, 1/2 e to the power of 0, which is just going to be a 1. So this ends up being e to the, just e, let's just say e minus 1/2 of e minus 1 plus 1/2. So these two just give me a minus 1/2. Right? Minus 1 plus 1/2 is minus 1/2. And I have 1 minus 1/2 just gives you a half. So it's just going to be 1/2 e minus 1/2, which we can just rewrite as 1/2 parentheses e minus 1. Good. Any questions? Any questions, any questions, any questions? Good. Okay, let's try another one then. Okay, so notice that for number 4, it almost looks like life is going to be easy here. But if we go in this direction, we have different rules for our rectangles, right? As I set up rectangles this way, in the middle, it'll be the red one. The red function is the top minus the blue one, right? In the middle part here, we get that. But out in the edges, look at this little edge over here. I would end up with a weird rectangle where the top and bottom are both the red function. And same thing over here, if I go this way, I would end up with a rectangle where the top and bottom are both defined by the blue function. So that makes it kind of confusing to figure out the heights. But if I tilt it on its side and think of rectangles that are this way, then we have the same rule going across the entire section. we'll have that the red function is always the rightmost function, and the blue one is always the leftmost function. Is that okay? Put some writing. Try and mimic that a little bit. So we have this problem. This function here goes like this, like that. And then we have another function that goes like this. And the colors don't matter, Okay, so in the middle, say somewhere like here, I have a nice pretty rectangle where it's the blue tells you the top of the rectangle, the black tells you the bottom of the rectangle, and so everything is fine there. But however, as I switch over here, I end up with these little areas where now the blue function defines the top of it, and the blue also defines the bottom of it, so that's weird. And then over here we have the same problem where on this side, this function, the same function, defines the top of it and the bottom of it, so that causes problems, right? We don't want to go in that direction. We don't want to do it that way. Good. This is bad. Okay, so what do we want to do instead? And again, remember my pictures suck, but this kind of goes like this, and this guy kind of goes like, oops, kind of goes like this, whatever. Okay, so what we want to do is we want to go across this way. We want to come up with rectangles that go this way, and then in the region of interest, we always have the same rule. The red function will define the roof, and the blue function will define the basement of it, the lower function, the leftmost function. Good. But if we're going to go in this direction, then that means that this is a little dy, right? And then that means that I'm looking for an x output. It would be some function of x whose output is x, and I want that to be the top one. And then over here, there will be some function of y, which gives me that bottom value of x, so that I can subtract them in that order. Good. Luckily, they already did that for us. This question gives us that this function here is the function x is equal to 2y minus y squared. Right? We input a y value, and the output is an x. And that's what this is going to be. This is going to be x sub t is equal to this. Good. And then they give us this guy over here, which is the blue function. The blue function is the x equals to y squared minus 4y, which is going to be that bottom function in blue. Good. Questions, 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 questions? Okay, so now we need to know these things here, and luckily that's a 0, but they also give you where they cross. They cross at -3, at -3, comma 3 is where they cross, and at 0, comma 0. Good? Okay, so then the area is going to be equal to the integral of, and I know, so when I set these up, I jumped to putting my little dy there so that I can keep track of the fact that that's going to be my limiting variable. That means that these are y's as well. They have to match. Little y's. Okay? And then as I do this, I need some, the red value function, which is an x of t, the top x value, minus the bottom x value, like that. But it's a function of y. So I need to input a y, and the output would be that value x of t. Good. Okay, so then the area, then just to kind of fill in the blanks, is going to be this integral. This would be 2y minus y squared minus the bottom one, which was y squared minus 4y. The whole thing is a dy. Come on, computer. The whole thing is a dy, and this ranges as y goes from 0 to y goes to positive 3. Okay? Going across here, this is a positive 3. Okay? So keep track of the variable of integration. Once we've set it up, now we just have to use our properties and rules to simplify life and work our way through this. The first thing I would do is distribute these and combine these so that we have something easier to work with. So the area is equal to the integral, as this goes from 0 to 3 of, that'll be 2y plus 4y. I distribute that, and then I'll get a minus y squared minus another y squared dy. So let's move that over here. The area will be equal to the integral as y goes from 0, y goes to 3 of 6y minus 2y squared dy. And that's a really easy integral. So let's see, that'll be using my guessing and checking. Let's see, that'll be 6 times 1/2 y squared. Now this part takes care of just the y, and there's a constant 6 there, so that'll reduce to a 3. Minus 2 times 1/3 y to the third. And that'll take care of that guy. And all of that gets evaluated as y ranges from 0 to y goes to 3. So the area is going to be equal to 3 times the 3 squared minus 2/3 times 3 to the third power minus, and it'll be 3 times 0 squared minus 2/3 times 0 cubed. Right, and of course this whole back part becomes 0. 0, 0. And this becomes x to the third power, and we have an x to the third power. So I'll end up with positive 1/3 x to the third power. Times 3 to the third power. Why do I keep, well, okay. Right. And then that reduces to just x to the second power, or 9. So 3 to the second power equals to 9. Right, so area equals 9. Any questions? No questions, no questions, no questions. I hate how messy this whole thing ends up looking. So why? Okay, we're good? Solid? Solid? So the concept stays the same. I don't think the concept is any more difficult, except that Here, for the first few of these, they gave you a nice pretty picture, and you could tell which is the top function, which one's the bottom function. With these other ones, it can get a little trickier to figure out which function is the top function, which one's the bottom function. Feel free to use technology to figure that out. So sketch the regions enclosed by the given curve, decide whether to integrate with respect to x or y, draw a typical approximating rectangle and label its height and width, then find the area of the region. Okay, so that's going to be the kind of the hard part here. You're going to have to graph it and figure out when the function is above, when it's below. Use your technology. I would recommend getting comfortable with your calculator, since beyond when we get back into the classroom settings, most teachers allow calculators, or in many cases you'll be allowed to use a calculator, and in many cases you won't be allowed to use a computer, but it is also really nice to use something like Desmos that helps you graph things. Okay, are there any suggestions on anything we should do next? Let's try a couple more. Those look all pretty straightforward, right? You just have to figure out which one's the function on top, which one's the function on bottom. Weird and tricky here. How about number 12? So this is chapter 6, section 1, number 12. So we have 4x plus y squared equals 12 equals 12. Okay, and we have x equals to y. So, how do we figure out what this is? Okay, so we can kind of get a rough sketch by trying to solve. Now, if we solve for y, we're going to end up with this square root thing, plus or minus square root of something. So instead, think of solving it for x, and you end up with 4x equals to 12 minus y squared. Divide everything by 4, and we get x equals to 3 minus a fourth y squared. And then just moving things around a little bit, I'll do this. 1/4 y squared plus 3. Right? If it was the opposite, case, right? If I had that y equals to negative 1/4 x squared plus 3, this would be a parabola, right? The fact that it's 1/4 means that it opens wider than the standard x squared function. So opens up a little wider. The fact that it's a minus means that it opens upside down and then shift it up. Good. But that's if we had it in terms of x. If we have it in terms of y, just kind of have to tilt your head and think about the how I would graph this way. So here, I'll put this one. If this was your standard xy function and I was graphing this one, put big if, then the fact that it is, let's put it this way, it would look something like this. It would be upside down because it's negative. It would be wider than normal because it's a 1/4. And it would be shifted up by 3 points, 3 units because of this plus 3. So instead, because it's an x equals y squared, then it's kind of tilted on its side this way. Right? And think about it, when y equals to 0, this becomes 0, and the output x becomes 3. So it's going to end up looking something like that. Good. And then we have the line x equals to y, so that's just going to be a straight line that goes like that. And you know what, let me extend this a little bit more. This is going to go this way, and this guy is going to, well, something like that. Good. So we want the area between the two. So we want this area here. And I could see that it makes sense to have rectangles that are laying down on horizontally this way, right? Because if I have rectangles in this direction, things make sense over here. It's always if I do it this way, it's the green one on top, blue one on bottom, right? Everything looks good, but over here, the little tip, I end up with a problem. I end up with the blue one on top and the blue one on bottom. So that's confusing. We don't want to do them that way. So let's go back here. And we want to go this way. If we go this way, then we always have the same rule. It's always going to be that this blue one is the far right one, it's the top function, and then that the green one is always the bottom one, right? Okay, so then that means that I'm going to want some sort of a delta y. Y is going to be my variable of integration. Let's okay, so then let's set it up. The area is going to be equal to some integral. The limits of integration are going to be y's. And my variable of integration is going to be a dy. And I just need to figure out the length of the rectangles. And it's going to be the x sub blue minus the x sub green in the way I have it, right? So I need some function of y that outputs this x value, that's the big x value, minus a function in y that gives me this value. Good. The green one's easy since it's x and y, no problem. So here, this is just going to be y. Right? Input y, what's the green? Well, okay, they're equal to each other. And that takes care of this, the smaller value. Now the bluer one, this one, we want a function where you input a y and the output is x, so we're going to want this guy. Good. So this is going to be the minus 1/4 y squared plus 3. Good. Just keep track of the fact that the variable of integration is y. I want to input a y that will output an x, right? This whole thing, when you input the particular value of y, the output is a value in x, that's this blue function, minus this function. Good. And the y is going to go from, the y ranges across these things from here to here. Right? So I want to know these two places. I need to figure out where they cross. When do they equal to each other? Good. Questions, 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 questions? Okay. So when do they equal each other? So let's do that over here. So let's figure out this right here. Okay, so let's say that that's some value a comma b. Right? There's some particular value there, some particular value there. We're looking for that b value so that they cross each other. At that point, that ordered pair is part of both of these two equations. Right? So at that point, a comma b, it must be true that a times 4 plus b squared equals to 12, right? Because it's a point on the blue function. It obeys those set of instructions. But it also must be true that the a equals to b, because it's on the green one. It obeys those set of instructions. Good. So we can just plug it in here and get our result. So a equals to b, so this would just be 4b plus b squared equals to 12. Okay, so then that means that b squared plus 4b minus 12 equals to 0, which means that b plus 6, b minus 2 is the way that factors. B squared minus 2b plus 6b gives you the 4 minus 12. Good. So that means that b plus 6 equals 0, or b minus 2 equals to 0. So b equals to 2 is one answer, and b equals to minus 6 is the other answer. So we can see from here, from our picture, that this must mean that this guy is a 2 here, and that this must mean that b equals to negative 6 there. Good. I found the two places where they equal each other. They equal each other when the b, the output, is negative 6. And just by the picture, I can see that it's got to be this one. And the other one is when b equals to positive 2. So going back to my integral, now I know that this must integrate as y ranges from negative 6 to y goes to positive 2. Right? From negative 6 to positive 2. Any questions? Now let me restate my area now that I know those values. So the area is going to be the integral as y goes from minus 6 to y equals to positive 2 of negative 1/4 y squared plus 3 minus y dy. Any questions, any questions, any questions? Now we have our integral all set up. That's the hard part. Once you have it at this stage, then you can just use our techniques for integration. And luckily, this is a really nice, easy integral. It's just a polynomial. So that area is going to be equal to negative 1/4. And then I'm going to have a 1/3 y to the third power. That takes care of that one. Plus 3y, that takes care of that one, minus a 1/2 y squared, that takes care of that one. And the whole thing evaluated as y ranges from negative 6 to y goes to positive 2. And so now we just have to be careful about how we apply these things. So this would be negative 1/12 2 to the third power plus 3 times 2 minus 1/2 2 squared. That takes care of applying the y equals to 2 minus, and then I have minus 1/12 negative 6 to the power of 3 plus 3 times negative 6 minus 1/2 negative 6 squared. Okay, so this will be negative 1/12 times 8 plus 6 minus, and that'll be 4/2, that'll be a 2. Just kind of chipping away at simplifying this. And this will be 6 times 6 is 36 times 6 is 236. Right, sounds good. 6 to the third power, about 216, not 36. 216 divided by 2 is 108. So this will be 108, and it's going to be negative. The negative gets preserved by the power of 3 times the negative becomes positive, and then there's this extra minus, it becomes negative. So lots of signs to keep track of. Minus 108. And this becomes minus 18, and then there's this minus to distribute, so it becomes plus 18. And then 36 divided by 2, right, we have a minus, so it becomes minus 18 plus 18. Good? Questions, 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 questions? Let's see, that's minus, that becomes plus, yep. That looks good, that looks good, that looks good. Okay, so 8 divided by 4 can simplify to 2/3, so minus 2/3. This becomes plus 4. Minus 108 plus 36. Minus 72, minus 68, 40, oh yeah, minus 68, okay. So this becomes negative 2/3 minus 68. So negative 67 1/3. Negative 67 1/3 as a mixed number. Something wrong. I feel like something's wrong somewhere. You have to catch it. Something's wrong somewhere. I'm getting a really big negative number. Negative, positive, negative. Did we catch something I did wrong? Ah, got it. No mistake here.
Should be.
Oh, you caught it? Should be what?
I'm going to say 4/3, but I'm not sure if that's correct.
My mistake is right here. So this is 12, and then I put 12 right here, right? And then I replaced the y with a 2, and then, right? So so this right here is the round where I replace all the y's with the 2. So this one should be identical, except I replace all the y's with a minus 6, and they're not identical. I forgot the 12. Right, so this should be, the correction is that this should be 12 there, not 2. So this is wrong. I'll just put it in. This is going to be 216 divided by 12. 12, which gets you to 18. That makes life a little easier. So this will be negative, positive, negative again, minus 18, and then minus positive 18, positive, negative, positive again. Okay, so then these two cancel out and we just end up with a plus 18. So we get a plus 18. Let's erase. It's going to be 2/3. It's going to be plus 4 plus 18. Which gives you 20 as a mixed number. Well, it's going to be 22 minus 2/3, which as a mixed number becomes 21 1/3 as a mixed number. But for some reason, math people don't like mixed numbers. Just make sure that's noted as mixed. Come on. Mixed. So that's really going to be 63/64/3. Good. That's our final answer here. The area is equal to 64/3. Questions, 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 questions? Good, good. All right, let's try one more, and we'll give up. Let's see. Any suggestions on any of these guys? Let's jump to something really fun. Let's see, 14. That's not bad. You just have to integrate that and integrate that. 16. Just have to figure out when they cross. 18. That's not bad again. No, none of these are really that bad. You just have to graph them and figure out when is one greater than the other. How about number 20? 20. It's going to be very, very similar to this one. They're all kind of similar to each other. Oh, so this is Chapter 6, Section 1. Oops, number 20. And we have x equals to y to the power of 4. And y equals to the square root of 2 minus x. And we want to use that and enclose it with y equals to 0. So looking at all those functions. So this one is going to, let's use technology to graph these. I can get a rough sketch. This is going to look something like this. See, this guy is going to look something like this, almost like a parabola, but like really square. Just kind of goes like that. Oh, that's really ugly. Anyway, it'll be something like that for this one. This one is going to look something like a root, except it got flipped and it's rotated about the y-axis because of this minus, and then plus 2 means it got shifted up. So this has something that looks like that kind of thing. And then y equals to 0. So we're interested in this region right here. And then, as you can see, we can break this up into two parts. We could figure it out by figuring out where they cross right there. And then we can separate this into two pieces and find area 1 and area 2. And in area 1, it'll be the blue function minus 0. Just integrate the blue function from there to there. And then for area 2, integrate from there to there on the green function. Good. So we just got to figure out a couple of these things. So first of all, that's important. Let's figure out, see if we can figure out when they cross. So at that point, there's some point a comma b, where the two functions equal each other. So therefore, at that point, we would have the case that a is equal to b to the power of 4. And it's also true that b is going to be equal to the square root of 2 minus a at that point. Right? Both statements are true. From here, we can see that that must mean that b squared must be equal to 2 minus a. So b squared plus 2 is equal to a. Wait, no, got this wrong. Moving the minus 2 over, it still has that minus, and then we've got to flip this around and distribute a minus. So we end up with a equals to 2 minus b squared, which we can stick right in here. So that means that 2 minus b squared equals to b to the power of 4, which means that 0 equals to b squared plus b to the 4th power plus b squared minus 2. So we could think of this as b squared squared plus b squared minus 2. And so if we let a simple substitution of, say, x equal b squared, we end up with 0 equals to x squared plus x minus 2. And am I losing something there? How does this factor? This factors as a minus 2 plus 2. So this will be x plus 2x minus 1. Factor that guy. Which means we can go back to our, oh, you know what? It was a really terrible idea to say my substitution is x. So let me get rid of that. I think that adds confusion since we already use x way too much. How about a nice w substitution? Let's let w equal to b squared. So therefore I can rewrite this as w squared plus w minus 2. Right, so I was just pointing out that this is a quadratic in disguise. It's one of our little tricks for factoring this. So we'll end up with w plus 2, w minus 1. That gives you this guy. So now we can go back to say that that must mean that w plus 2 must be 0, or w equals negative 2. But w was equal to b squared equals to negative 2. What value of b exists so that if we square it, it gives me a negative? No such thing, right? So no solution from here. No real solution. We'd end up with square root of negative 2, right? So root 2i would be the solution here. B would be equal to I root 2, plus or minus. But we're not dealing with imaginaries at this point, so we would just drop it. No real solution. Good. The other one would be that w minus 1 equals 0, or w equals to 1, and so b squared equals to 1, and so b equals to plus or minus 1. Okay, so now looking at our picture here, well, it's going to be positive 1. Right, so after all that work, I confirmed that the place where they cross must be the point 1, comma 1. 1, comma 1 is A, B. Right, let's just make sure it makes sense. Sure, if we let 1 there and 1 there, yeah, 1 to the 4th is 1, so 1 equals 1, so this would be a true statement. And if we put a 1 there, 2 minus 1 is 1, square root of 1 is 1, so we also get a true statement. So yep, that must be the point 1, comma 1. Good. Questions, 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 questions? Okay, so let's set up both integrals, and and solve it in both directions and see which one you like better. So as I said, one way to do this is to separate this into two separate integrals, area 1, area 2, and find our answer from there. And we also need to know what this is. So this is going to be the point 2, and this is going to be the value 1. Right? So we'd have to separate it, and this is 0. Good. So the entire area, the total area, here. So the area is going to be equal to area 1 plus area 2, total area. So this will be equal to the integral, and I'm going to integrate in this direction. I'm going to make rectangles that go up and down. So it'll be a rectangle this way and a rectangle this way. So for area 1, I'm going to integrate with respect to x. Here's x, here is y. My little d, my deltas are going to be delta x's, x's. So I'm going to have a dx for area 1, dx. And x is going to range from 0 to 1. Questions?
No.
Guys, questions? And you watch your mic? I think we have a hot mic situation here. Okay, so this guy is going to be a function of y. Right? I need a y as an output for x as an input. So I need to solve for this, and I end up with x to the 1/4 power. This is the fourth root of x dx. That's going to be this blue one. And it's positive, right? So I don't have to worry about the minus part. It's positive. Good. And for the green one, that's this one. So I'll end up with plus the integral as x ranges from 1 to x goes to 2 of the green function, which is equal to square root of 2 minus x dx. Any questions about that setup? Good. Right. So in each case, this is a function of x. The output will be a y. The output will be the height of the rectangle in that little region. Okay. So then to solve this, I'm just going to rewrite this as x to the power of 1/4 dx plus this, which is equal to the integral as x goes from 1, x goes to 2 of 2 minus x to the power of 1/2 dx. Okay, so this is going to be guessing and checking here. I know that I would normally subtract 1, so something I'd have to add 1, so this would be 5/4. The derivative of this, bring down that constant, subtract 1, or subtract 4/4, gives you positive 1/4. So we just have to multiply this by 4/5 out here, times 4/5. And this gets evaluated as x goes from 0, x goes to 1. Plus, now this guy, let's guess and check that a little bit. Again, I need something that has 2 minus x to the power of 3/2. So I add 1. So taking the derivative of this, I would bring that out in front, and I want that to cancel, so let's multiply it by a 2/3. Minus 1 gives me that. So I have this. Now the chain rule will still give me an extra minus in here. So I know I have to multiply that by a minus out there. That gets evaluated as x ranges from 1 to 2. Good. Questions? Okay, so let's evaluate all of these guys. I get 4/5. I'm going to just kind of factor that out. And then, since it's a constant, and then I get 1 to the power of 5 over 4 minus 0 to the power of 5 over 4. That's going to be easy. And then I'll have a minus 2/3 factored out. And now it's this thing, which is going to be 2 minus 2 to the power of 3 over 2 minus 2 minus 1 to the power of 3 to the power of 2. Good. Some stuff simplifies. That's just going to be 1. And that's just going to be 0. And that's going to be 2 minus 2 is 0. 0 to the power of anything is 0. So that's just 0. And 2 minus 1 is a 1. 1 to the power of 3 over 2, that's still going to be 1. So life simplifies quite a bit here. And we end up with 4/5 times 1 minus 0. So just times 1 minus 0. Minus 2/3 times 0 minus 1. So I get 4/5 minus plus 2/3. Good. Okay, so common denominator is going to be 15. Let's multiply this by a 3 over 3. Multiply that by a 5 over 5. And I'll get 12 plus 10. 12 plus 10 over 15, or 22 over 15, and that'll be my whole area. So my area equals to 22 over 15. Any questions? Questions? Okay, so that's method 1. We broke up the area into 2 regions, area 1, area 2. We figured out where we need to break it up to, so we have to figure out this value of a there. And so we had area 1 integrating the blue function from 0 to 1. That gives me this thing. And this is the function of the blue one. Okay, just to make sure it's clear. This is that blue function. So that takes care of this first part. And then this one is the second one, which is the green one. Right, so that takes care of the area between x going from 1 to 2, x going from 1 to 2 of the green function, and my derivative is dx. Right, so my rectangles are this way, and the limiting variable that I'm going to integrate over is x. Right, so all of these are little dx's. All of these things are little dx's, which results in delta x's, which results in a little dx when I integrate. Good. Okay, so let's do it the other way around now. You don't have to do it both ways, but it's nice to practice doing them so that we can be ready for it if we need to. Sometimes you'll have no choice. You'll have to do it one way. Often it's just a matter of, one way is easier than another. Come on, over there. So we have a blue function and a green function. So the green function comes in like this, and then the blue function was one that went like that, and then this way. Okay, so we were just interested in this little part here. Okay, so the other way we could do this is to think of rectangles that go in this direction, like that, which means that for each rectangle, we'd always have the same rule. The green function determines the top, the rightmost value, and then the blue function always determines the leftmost function. For each one of these rectangles, now we would be having a little dy, a little delta y, which means I'm going to integrate it and get a dy, right? The limiting variable. I want to make these little deltas as small as possible. Good. So I need to figure out this x sub top value there, and then I need to figure out this x sub the bottom one right here. And again, this is the x from the blue one, and this is the x from the green one. Good. Writing down their equations, for the green one, the equation was y equals to root 2 minus x. But this is written in a form where you input the x, calculate some stuff, and the output comes the y. Right? We're going to want it in the other direction. I'm going to want to input a y so that I can output my x. I need to solve for x. So if we solve for it, we get 2 minus x like that. And so we get x equals to 2 minus y squared. And now it's written in a form where we input a y value. Given a y value, we can trace it back to its x value, right? In this little region, the way we've drawn it. And of course, we only care about its positive result. Good. Questions? Okay, and now the blue function, the blue one was given as y equals to x equals to y to the 4th power is how it was presented anyway, and that's how we want it. We want to input a y, output is an x. Okay, so now I'm ready to set up my integral. The total area is going to be the integral of, remember I like to put my little dy over there so I don't get confused, and then that means that these must match up. Okay, and then I want the biggest one minus the smallest one. The biggest one is going to come from the green one, so that'll be 2 minus y squared. That'll be my top x value, the one that comes from the green, minus the smaller one, which is this one that comes from the blue, so it'll be a minus y to the power of 4. And then the whole thing has times dy. And then the limits of integration, they're going to go from here to there, right? This point right there where they cross. The y, the delta y, is going to change from 0 up to there, and we had already established that they cross at the point 1, 1. So they're going to integrate this way. So this will go from 0 to 1. Good. So we have our setup. We need to figure out what this is, and hopefully this integral gives me the exact same answer as the other one. It should. So the area is going to be equal to, well, it's a nice, pretty little polynomial, right? So this is just going to be equal to 2y minus 1/3 y to the 3rd power, that takes care of that guy, minus 1/5 y to the 5th power, that takes care of that one, evaluated from 0, y goes from 0 to y goes to 1. Okay, so it should be a nice, easy little polynomial to evaluate. 2 times 1 minus 1/3 times 1 to the 3rd power minus 1/5 times 1 to the 5th power. And then the 0, well, that one's easy. That's just going to be 2 times 0 minus 1/3 times 0 to the 3rd power minus 1/5 times 0 to the 5th power. All of that disappears. That's just 0, that's just 0, that's just 0. So that just disappears. And 1 is easy as well. So my area is going to be equal to 2 plus a third minus a fifth. Good. Common denominator is going to be 15. So let's figure out what that is. Multiply, put a little 1 there. Multiply this by 15 over 15. Multiply this guy by 5 over 5. Multiply this guy by 3 over 3. And we end up with 30 plus 5 minus 3. Oh wait, that's a... Why is that a plus? That should be a minus. Sorry, right here. There should be a minus. There's a minus there and a minus there. So there should be a minus there and a minus there. Okay, so it should be 30 minus 5 minus 3 all over 15, which leads to exactly the same answer we had before, 22 over 15. Area equals to 22 over 15. Any questions? No? We're good? We're good? Okay, that's a good place to stop then, and I guess I'll see you on Thursday then.